Okay, good afternoon, everybody. I am George Christian, and as I've been already introduced, I am a co-founder of Aliena. And probably you've heard yesterday the talk of my colleague from Aliena, Mark, about propulsion systems. I am indeed pursuing my PhD at the moment in plasma propulsion systems at the Nanyang Technological University here in Singapore. And today my talk is going to be about objects that are a bit farther away from us than our beloved moon. You are going to embark into a journey together with me across the electromagnetic spectrum. We are going to learn what the electromagnetic spectrum it is. And during this journey, we are going to see how colorful actually the universe is. And we will also try to understand how can we perceive the invisible universe, right? So my talk is going to be about satellite instrumentation for astrophysics, which is actually my major. I came from this field, and then I shifted towards propulsion. So we are indeed surrounded by waves, right? As we speak, we are bathing into electromagnetic waves that are bouncing on and off our bodies, right? TV waves, radio waves, the famous microwaves, even the light itself, even if it comes from a light bulb or from a star or from a candle, it's an electromagnetic waves. X-rays, when you go and make a radiography, or even your brains at this point, they are emitting electromagnetic waves. Most of those electromagnetic waves are actually harmless, right, if they have very low intensity. But some of them can be very, very dangerous because they can penetrate through our tissues and can cause damage to our DNA. Now, what's actually an electromagnetic wave? I will go into a bit of physics, so just hold on with me for a while. It's not going to be very, very difficult, I hope. So the good old physics tells us that any charged particle, either positive or negative, is going to create an electric field around itself. Now, this electric field, you can't actually see it, unfortunately. The only way is to sense it. And how do you sense it? You sense it only if you are another particle, like this little body that gyrates around those two opposite charged particles, right? If we force those particles to have an organized movement through a conductor, let's say a wire, right? This movement is going to be called electrical current. And now this current through this wire is going to produce in turn a magnetic field. Now hold on, the things become a bit even more deeper. If we try to oscillate this electric field, right, let's say by bouncing a particle from up and down, we are going to make an oscillating electric field. Now, this oscillating electric field is going to produce an oscillating magnetic field, which in turn is going to sustain the electric field, right? And in the same time, is going to produce the famous electromagnetic waves, which has an electrical component and a magnetic component perpendicular to each other, right? So that's why we call it electromagnetic wave, right? Electrical magnetic components. And those waves, they travel very, very fast through space with the speed of light, which is a lot, 300,000 kilometers per second. That's a lot. Now, the electromagnetic wave, they have the same properties like any other wave in the universe, right? And those properties, they help us in classifying those waves, right? And in constructing the electromagnetic spectrum. Now, the properties of those waves, they are very linked to each other. For instance, the wavelength is defined as the distance between two crests, right? A wave has crests and dips, ups and downs. So the distance between two ups or two downs is called the wavelength, right? Long wavelength usually have low frequencies. Why? Because the transition of those crests is very slow in time, as you can see in the first... does this work? As you can see here, right? The transition is very slow. Now, if the wavelength is short, then the frequency is higher, the transition is very, very fast, and also the energy is much higher, right? Now, the electromagnetic spectrum, probably, I hope that everyone is already familiar with a very short part, a very small part of the electromagnetic spectrum, which is called the visible spectrum, or the famous rainbow up there, right? This portion of the electromagnetic spectrum, it is the only one that can be perceived by our vision. So wavelengths from red to blue can be perceived by our vision. Everything else on the slide can't be seen, unfortunately, right? In order to those visible wavelengths, right? They have the wavelength of the waves has the size of a bacteria, and the energy that they are carrying is very, very low. In order to emit this kind of visible light, your temperature should be around 2,000 to 10,000 degrees centigrade. It's quite hot, right? But as I said, there is much more out there. There's much more out there besides this rainbow, right? We speak about wavelengths. We speak about waves that have wavelengths bigger than the visible wavelengths, right? Infrared, microwave, radio waves. All those, they can have wavelengths that span from the tip of a needle point, the tip of a needle, up to a few kilometers, right? And they usually have very, very low energy. Now, on the other side, the ultraviolet, maybe you've heard about them, X-rays, I hope you heard about them, and also gamma rays, they have very high frequencies and they can carry a lot of power, a lot of energy. So they can be very, very bad for for the human lives, right? Now, we've always been fascinating about the sky, right? And we were always, since forever, looking at the sky. And we have been fascinating, especially by the objects that are very, very close to us. The sun, the moon, and the planets, especially Venus and Mars, right? Astronomers, ever since antiquity, they try to come up with a lot of mathematical laws that can predict their movements and their future occurrences, right? But there was only in the Middle Age when someone actually looked at the sky through a telescope. And that guy was Galileo Galilei, which looked for the very first time through a very tiny telescope. And what did he do? He managed to look very well at the Jupiter's moon and also discovered some of them. And those moons nowadays, they still bear his name, the Galilean moons, and some of them are even bigger than the Earth. So they are very, very big moons. But a bit more than 60 years ago, humanity managed to send the very first artificial satellite into space, Sputnik 1, right? And ever since this thing happened, the evolution in space technologies was so fast and tremendously changed our perception about the universe, right? And it didn't take too long when we figured out that why not onboarding telescopes into satellites and put them on orbit. And from that moment on, we realized that there is so much more out there and can give us enormous information about our past and especially our future. Now, why should we move the telescopes out there? I told you already that most of the radiation, we can't actually see it, we can't actually perceive it from the ground level, right? And now, the second reason, which is the most important reason, is the fact that our atmosphere behaves like a blanket, which absorbs most of the radiation. Visible light, right, a part of the infrared and some radio waves, they can pass through the atmosphere up to the ground, and we can see it, right? We can see the sun, we can see the stars that are invisible light. However, microwaves, most of the microwaves, the ultraviolet, X-rays, and gamma rays, they can't pass through the ground, they can't reach the ground. And thanks God this is not happening because they are very, very bad for our skin and for our DNA, right? So that's why we managed to put our telescopes up in space so that we can see all those things. Now, just let's embark into our journey that I promised to you today, for today. And we start, obviously, with the visible universe. We are going to see some very beautiful pictures today. And I hope you're going to enjoy the colors of the universe. Now, the visible universe, this map, it's actually a 3D map of the entire sky. So almost the entire visible universe is in there. Of course, it's a 2D picture here, and it was made with the same principle that we are making 2D geographical maps, right? The Earth is a sphere, it's a 3D object, but we managed somehow through mathematical operations to transform it into a 2D map, and we can read the map. The same here with this map of the entire universe. Now, on the center of the map, right here, probably you are already familiar with the image of the Milky Way, which is our galaxy. This here is where we are living, actually. So the visible universe, in order to take pictures of the visible universe, the wavelength that we are looking at, it's around 0.5 micrometer. To understand how small this is, I will just tell you that the human hair has a diameter 100 times bigger than that. So it's very, very, very small, right? What can we see in this map? We see a lot of hot objects. We're speaking about stars, we're speaking about star explosions, about galaxies, and about huge clouds that are extremely hot. And in those clouds, actually, the stars and the planets are born. The stars are of particular interest for us. Why? Because more than 99% of the entire mass of the universe is concentrated in stars, actually. And they are very important for us. Why? Because they are usually orbited by planets. And some of those planets, they are just at the right distance away of those stars in a zone that we call it the habitable zone, like our home, the Earth. So those planets, they might have life, or they might be able to support life. Now, stars have colors. That's a very nice thing. And the rule says that the hotter the star, the bluer the color. The cooler the star, its color is more towards red. Our sun, it's yellowish, which means that it's almost somewhere in the middle. And this is because it's a middle-aged star, so around 45 years old, right? And its surface temperature, it's around 5,000 to 6,000 degrees centigrade. Now, why do we study all this? As I said, we studied it because stars have actually a life cycle. They are like human beings or like living beings. They have a life cycle from birth through their middle age, right, through maturity, and finally death. And the death can be very, very interesting, right? Either by explosions or by tremendous collapses. Now, let's move on our journey, and now we are going to a part of this electromagnetic spectrum that allows us to see very cold objects. So we are going towards infrared and microwave spectrum, and we are looking at long wavelengths, therefore low frequencies and very low energies. And the first stop is the infrared universe. Now, we managed to make a lot of detectors that allows us to see the infrared universe, and we got an unprecedented access to very low temperature objects. What are those objects? Those are dust, molecular clouds, atomic hydrogen clouds, and also protoplanetary disks. What are those protoplanetary disks? Those are actually all the matter that is around a star, and from this matter, in time, the planets will be formed. So the information from an infrared observation of the universe is extremely valuable because it shows us how the solar system came into existence and what's the future of the solar system, how Earth came into existence, and how other Earths out there may exist. So this kind of astronomy in infrared helps us in our continuous search for extraterrestrial life and for exoplanets, right? Planets that can maintain life. Now, every single one of you emits infrared radiation as we speak. And because your temperature is around 36 to 37 degrees centigrade, the frequency that you are emitting, the wavelength that you are emitting, it's about 10 micrometers. And this is almost the same wavelength like the wavelength in this picture, which shows huge molecular clouds around our galaxy. Now, in this picture, I give you two examples of the Milky Way, our galaxy, and the Orion Constellation, in visible and infrared. You can see that in the visible images, more or less everything is dark, but when we are looking at the infrared images, they are much more lively. A lot of things are happening in there that we can't see them with our vision. So in the case of Milky Way, we can see that there is a lot of activity, especially in the galactic plane, in the center, right? The center of our galaxy emits a lot in infrared. Also, there are a lot of clouds, and all those clouds are extremely important because there is where stars born, and there is where planets are born as well. When it comes to the Orion Constellation, the differences are even more striking because this region of the universe is known as being one of the most active in the entire universe. You can see those huge clouds of molecular compounds and hydrogen that are actually the nursery of the future stars and planets. Now, a very interesting radiation which lies at the limit between infrared and microwave. This radiation, which has a wavelength of about 1 millimeter, very, very small, but still we can see it, right? We can measure it. This radiation, which is called the cosmic microwave background, it's actually the landmark evidence of Big Bang theory of the formation of the universe. So I don't know how many of you think that the Big Bang is just a theory that probably wasn't ever proved, or it's something that crazy astrophysicists think that it's true. Well, it's actually true, and this proves that, yes, the universe came into existence through Big Bang. And this radiation, it's actually a relic radiation. What does this mean? It means that it comes since the formation of the entire universe, and it fills up the entire space. And the spectrum of this radiation corresponds to the spectrum of a object that it's at minus 270 degrees centigrade, which is very, very low, very close to absolute zero. Absolute zero, it's actually minus 273.15 degrees centigrade. You can't be more colder than that. That's the absolute zero. So that's the cosmic microwave background, and I'm pretty sure that every single one of you, probably not the very young ones, but the ones like around my age and a bit older than me with the classical TVs, they've probably seen this radiation in the static noise, static TV noise, which actually contains about 1% of this cosmic radiation background. Now, let's move on to something more interesting, to the hot universe, right? To short wavelengths and high frequencies and higher energy, a universe that is much more alive and many things happening there. We don't start with something that is very alive. We start with the ultraviolet universe, and you are going to tell me that in that picture it's a bit boring and nothing really happens there. But I'm telling you that the ultraviolet astronomy is probably one of the most important branches of astrophysics and astronomy nowadays. Why? Because ultraviolet universe gives us a lot of information about new stars and new planets. And this is what humanity searches out there, searches new planets where it's possible that we can go and colonize and continue our species. Why? Because at one point, the Earth is gonna unfortunately die. And it's not something that we are gonna destroy it. Probably let's hope we don't destroy it, but at one point our sun is gonna explode, and anyway, the Earth is gonna disappear. So that's why we are continuously looking for this kind of new places where to go and live, right? So this is the ultraviolet universe. All those little dots that you see on those maps, there are actually regions where very young stars, let's say that those stars are in their 20s, those stars are living in there, and they are very important for us because they are not yet middle-aged like our sun. So it gives us a lot of information about the past of our sun and of our planetary system, right? So as I said, ultraviolet is very important for the exoplanets, right, to study their atmosphere. And they are also extremely important because most of the common matter, right, the physical properties and chemical composition of the common matter, and now the common matter, bear with me, it's also called baryonic matter, a very fancy name for the common matter. It's actually everything that surrounds it, that's baryonic matter. So this common matter, its properties are best studied in ultraviolet emission. Now, here we have an image of Andromeda Galaxy. It's a very interesting galaxy. Why? Because most of the planetary systems there are very young, very, very young, younger than ours, right? And looking at those pictures, we can understand how those protoplanetary disks, right, which contain the matter of the future planets, how they evolved from being very active into cold infrared emissions of planets later on, and how gravity actually plays an important role in all this process, how gravity makes planets get alive, right, and gyrate around the stars. So this is a very, very important thing, and Andromeda Galaxy is the best place to study. And you can see here on the bottom picture that it's a preview of our next destination, which is the X-rays, and we can see that just a few objects are emitting in X-rays, right, compared to the ultraviolet. It's a big mess in here. But here, no, just some of them. Why? Because they are hot enough in order to emit such strong radiation as the X-rays, right? Now, just like a side note about this pretty Andromeda Galaxy, this galaxy is the closest galaxy to our galaxy. It is at just 2.5 million light years away. 2.5 million light years away, it's a very, very short distance at a universe scale. So it's very, very close. And now, brace yourself, this galaxy in 4.5 billion years from now is gonna collide with the Milky Way, unfortunately, and in a tremendous clash that is gonna give birth to a new gigantic elliptical galaxy. But that's going to be a very, very long time from now. But yes, in the end, our galaxy is going to disappear as well. Now, how do we actually see and collect data for microwave, infrared, visible, and ultraviolet, right? There are a lot of telescopes out there in space that are already collecting data, and all the pictures that I've shown you today, they were constructed departing from data collected by those telescopes. We use reflective optics for that. So classical mirrors, like the parabolic mirrors that probably you use for your TV satellite, right? For your satellite TV, sorry. that kind of optics, right? Classical optics mirrors. But the detectors, they are also pretty much standard. We are using CCD cameras, which are not very far, very different than the CCD cameras of the very smart smartphones. The only difference is that they are extremely sensitive, right? Now, you have to keep in mind that when we are looking at infrared and microwave in particular, we are looking at objects that are very cold. So in order to sense the radiation that comes from those objects and distinguish it from the background noise, our detectors should be placed at an even lower temperature. So what we are doing, those satellites, they are usually placed at a very long distance away from the Earth. So the infrared emission of the Earth doesn't interfere. And we also keep all those detectors at very low temperatures, up to minus 270 degrees. Now, we are reaching a place, a portion of the electromagnetic spectrum which is quite dangerous. Gamma rays and X-rays. Why it is dangerous? We call it ionizing radiation. I will tell you later what does ionization means. But what I want you to understand at this point is that both X-rays and gamma rays, and also some very strong UVs, they can penetrate through matter, which means that they can penetrate through our tissues and they can make a lot of damage to our DNA, and they can break the bones of the atoms and can destroy matter. Fortunately, as I said before, the atmosphere is mostly opaque to those kind of radiation, so they don't reach the ground, so we are safe here. Now, physics lesson, now you really have to bear with me because this is a bit more complicated, but I'm pretty sure it's not going to hurt. The baryonic matter, and now you all know that the baryonic matter, it's everything that surrounds us, yeah, the fancy name for it. It's formed of atoms. An atom actually has a nucleus and electrons that spin around this nucleus, right? Now, if an atom loses an electron, it becomes an ion. And this process is called ionization. Now, how do we make atoms to lose their electrons, sorry? This can happen if an X-ray or a gamma ray hit the matter. Now, depending on how energetic the X-ray or gamma ray is, there are different effects that can be seen. The first effect is ionization. And because those electrons now, they are stripped of their atoms, they are free and they can conduct electricity, which means that they can be sensed through photoelectric effect. This photoelectric effect was discovered by Einstein, and he got the Nobel Prize for this. So Einstein got the Nobel Prize for the photoelectric effect, not the theory of relativity, yeah? Now, if the incoming X-ray and gamma ray are a bit more energetic, they will just pass through the matter and get scattered out of the matter, right? Of course, producing a lot of damage in the matter. And this effect is called Compton Effect. I'm not going to get into details. This is really quantum physics already. And now, the last one. If the gamma ray, right, it's extremely powerful. What it does an effect that is called pair production. When this radiation is going to hit my atom, a pair of electron and positron is going to be produced. Now, electrons, we know what they are. They are negative charges. They spin around the nucleus of the atoms, right? So those are the electrons. They conduct electricity. They are the ones that produce electricity, right? They conduct it. A positron, it's actually the antimatter counterpart of the electron. So it's not baryonic anymore. It's something else. And it looks identical like an electron, but instead of being negative, it's positive, right? Those positrons, they are positive, right? They will immediately clash with another electron, very close electron to them. And this clash can produce tremendous energy. And it produces a tremendous energy at a specific emission line, which is called the annihilation energy, right? Or annihilation gamma rays. Now, to have an understanding about those energies, I was speaking about energies, but just for you to visualize what energy means, I will just say that, for instance, visible light, right, the one that comes from the light bulb, carries around 1 electron volt of energy. Now, electron volt, it's another unit for energy, like calories, joules, watts, maybe you know those ones. Probably calories, right? That's energy. Now, this is electron volt. X-rays carry 1,000 times more energy than the visible light. And gamma rays carry 100,000 times more energy than the visible light. So they are extremely powerful, and now you can understand why they just simply pass through you, right? Now, when you go to the doctors and get a radiography, they will use soft X-rays. The universe is extremely abundant in soft X-rays, and this is because all the stars, they have an atmosphere around them, and all those atmospheres emit in X-rays, right? But not only the stars emit X-rays, or the atmospheres of the stars, also very hot structures emit soft X-rays. And we are speaking about supernova remnants, which are big explosions of big stars, or neutron stars, which are the big star, instead of exploding, it collapses and form a very, very dense object called a neutron star. So all those things actually help us to understand how the life of our sun is going to look like. Because at one point, our sun is going to grow more and more and more. It's going to eat Mercury and Venus. Probably, let's hope it's going to stop by the edge of the Earth. And from that moment on, our sun, most probably, it's gonna explode. But there are chances that it's gonna also collapse and form a neutron star. Unfortunately, our sun, it's medium size, so they don't really know yet what is gonna happen with it. But this kind of information that comes from the satellites help us a lot to understand how other stars behave. Now, not only those scary things emit soft X-rays. Also, due to the solar wind charge exchange, and I will explain what's that, the moon, comets, other planets, asteroids, they emit soft X-rays. Even our planet, the Earth, emits soft X-rays during the aurora events at the North and South Pole, right? During the Northern Lights. Maybe you've heard of them. So what's happening? The solar wind, which contains a lot of energetic particles, when they hit the atmosphere, there are a lot of processes that happen in there, and soft X-rays are emitted. Now, how can we see X-rays if those X-rays actually pass through matter? How can we collect them, right? We can still use reflective optics at this stage. It's the last point when reflective optics can be used. But we are not going to use those big dishes, those big mirrors. We are going to use another kind of systems, which looks like some nested foils, right? One after another, which help in focusing the incoming radiation towards the detector. Now, those foils, they can sense only the radiation that comes straight into them, so at very low angles. Everything that comes from above or from below is gonna just simply pass through the foil. Now, the detectors can be also CCD cameras, a bit more sophisticated than your smartphones this time, but also some more sophisticated instruments like the ionization chambers or the proportional counters or scintillators. All those things are actually devices that help us to, when the X-ray hits this device, it's going to produce a lot of electrons, which is converted in electric current. And then we can measure that current. And we know, yes, that current comes from that ray, which has this energy, right? Now, X-rays, we are looking at objects that are very hot. So our detectors, they don't need to be cooled down. I mean, if they are at room temperature, it's fine. But we still cool them down to temperatures up to minus 170 degrees in order to improve their efficiency. We are almost reaching the edge of the electromagnetic spectrum. We are moving to hard X-rays. Those hard X-rays are usually produced by even hotter structures. We speak about young supernova remnants and neutron stars. When you are young, you are very, very hot. When you get older, you get cooler, right? So hard X-rays, very young supernovas and neutron stars. Also, they are produced by very, very energetic cosmic explosions. And we are talking about a specific thing which is called, I don't have it here, I think it's the next slide, the cosmic rays. I put them under the nuclear gamma rays. So now, also, another important object in space produces hard X-rays and gamma rays, and those are the black holes. You've heard about them. Those black holes, we call them compact objects. Why? Because they are so heavy that their gravity is so powerful that they can actually distort and trap the light, so nothing gets out of them, right? But hard X-rays, they are extremely energetic and they can easily escape. So if we look at those maps, right, especially this one, And also those up there probably they are just young supernovas and neutron stars. Here we can identify some black holes. And this is very, very important information for all of us, because those black holes tell us a lot of, give us a lot of insights about how the universe evolves, and if those black holes are somehow connected and they appear in a specific region in the universe, right? Now we are really almost at the edge. And we are going to speak about nuclear gamma rays, right? They are extremely, extremely powerful. And those gamma rays, they are nuclear. Why? Because they are produced during the nucleosynthesis of chemical elements. So what we did right now, we moved towards very, very hot structures. And in the same time, we traveled back in time to the formation of chemical elements. So those chemical elements, they are produced in stars, in supernovas, right, through nucleosynthesis, which are nuclear reactions. During those reactions, tremendous energy is released in form of gamma rays. Now, a breakthrough for the gamma rays astronomy was actually I think I'm running out of time. Can I get more 5 minutes? Okay, great. So a breakthrough for the gamma rays astronomy was actually the first all-sky map of aluminium-26. Now you're going to ask me why aluminium-26, what's the fuss about it? Aluminium, you know that it's an inoffensive metal, right? But aluminium-26 is not. It's a radioactive element, and it's a radioactive isotope of aluminium. And this aluminium-26 has a specific energy line, right, at a specific frequency, the same as the electron-positron annihilation line. Well, those two lines, the astrophysicists, they use them to calibrate all their spectra. So they are very, very, very important for us. Now, high-energy gamma rays, those are the highest detectable radiation that we can detect. So it's in the range of 1 giga-electron-volts, which is 1 billion times bigger than the energy of the visible light. It can be produced by pulsars, which are very, very active stars, or supernova explosions, like you can see here. This is actually a supernova remnant. And globular clusters here. There are regions in the universe with a huge densities of stars, and those stars interact to each other and produce very, very strong gamma rays. How can we see hard X-rays and gamma rays? We can't use normal optics anymore. We can only trace them. How do we trace them? The ray will hit your detector, and it's going to produce a signal, and then we read that signal, and we understand what was the energy of the incoming wave. That's the only way. We have geometric optics, but they are not really optics, right? Quantum optics and wave optics. I don't want to go into details for this. I'm running out of time anyway. But what I want you to tell is that there are many, many satellites out there. I mean, not many, but a few of them that are already working and collecting hard X-rays and gamma rays. And most of the pictures I've shown you today were constructed departing from data collected by those satellites. Now, I think it's time to sum up everything. We've been on a journey across almost the entire electromagnetic spectrum, and you've learned that the electromagnetic spectrum is not just the visible part, which is very, very small, but it's also about the infrared microwaves, right? Very long wavelengths, low frequencies and very low energies, and also ultraviolet, X-rays and gamma rays, all of them having very short wavelengths, high frequency, and carrying tremendous energy, right? We also learned the fact that we can use total external reflections, right? Either mirror telescopes or those specific nested telescopes in order to see everything up to soft X-rays. After that, we can only track. We can't actually collect and detect, right? For gamma rays and hard X-rays. Now, we've also learned today that it's the lesson that we've learned today, it's also the fact that the atmosphere behaves like a blanket, and most of this radiation is shielded, right? Especially gamma rays, ultraviolet and X-rays, which are quite dangerous. And the only way to see and sense those radiations is to go up there in space, so we have to onboard our satellites, our telescopes on satellites. And probably the most important lesson for today is the fact that all those pretty images, right, all those pretty paintings, they actually help humanity to understand where do we come from and where we are heading to. So this is the most important lesson that we've learned today. Okay, now, I don't know if any of you actually wondered how how I was able to show you all those things when they are invisible in the first time. I mean, if they are invisible, how can we see them? Anyone? Any idea? No? Well, I will just tell you that it's a very, very nice trick that astrophysicists and scientists did. All the images that I showed you today are actually artificially colored. They are not like that. They are artificially colored in order to let you understand which regions are of high intensity or low intensity at a specific observation wavelength. That's why probably I can call the astrophysicists as very, very skillful artists. Thank you very much for your attention. If you have any questions, I'm pleased to answer.
Oh, okay, sure. I want to ask the 5G, where does it stay in the spectrum?
You mean 5 giga-electron volts?
No, the telecommunication 5G.
Oh, that's... To be honest, I don't really know, but I think it's gonna be somewhere in the microwave or even right away. I think it's microwave. Yeah, somewhere there. Yeah.
How about
I mean,
next?
all the phones are in microwaves. Yeah.
Yeah,
It's
hi.
microwave
I would like to
radiation.
ask a question. If a planet far away emit maybe a X-ray and is far away, when it reach your space telescope, will it reduce to infrared or UV? Reduce its frequency?
No. They lose in intensity, so those waves can lose in intensity, right?
I mean the power? Yeah.
The power that carries, yeah, but the frequency remains the same. The frequency is not going to be altered, yeah. So in the end, it's still going to be planets don't emit planets can't emit X-rays. What I told you about the Earth emitting X-rays is actually the atmosphere upon interaction with the solar wind. But the Earth itself doesn't emit X-rays, right? Or the moon, right? No, the dust around the moon emits X-rays.
Hey, so what is the next big step in the advancement of looking out into the stars and the universe in terms of detection? So people have already looked at the whole spectrum, really. Is it just about sort of refining that, making it more sharp images?
Yeah, definitely. The big step, I will show you the telescope that was not launched yet, which is called the James Webb telescope. And this telescope is going to replace the very old Hubble telescope. Probably you've learned about Hubble telescope. Some of the pictures, actually the visible spectrum pictures are from the Hubble telescope, right? So actually, yes, you were right. The trend is to make them even more precise, right? For instance, when we are looking at this kind of microwave infrared or any other type of radiation, we have like, when we look at the image, at the detected radiation, we have some peaks. And those peaks, they can be very broad, which means that they can be at whatever frequency or energy, right? So what we want those peaks to be very, very sharp, which means that we are sure that that thing from there emits at this specific energy, right? So that we can interpret the data and we don't have any doubts about, well, maybe it's something else there that emits next to it or things like that. And when it comes to looking at all those, infrared, and definitely from a cosmology and cosmogony point of view is to understand where do we come from and where do we go, right? I mean, physically, what's going to happen with the solar system and everything. But the most important thing, and I stretched it many, many times during the speech today, is the search for extraterrestrial life. That's one of them. But not directly, I mean, to see the bacteria or the life that happens in there. No, to understand if those places, those new places can sustain life. So they have, oxygen and water and molecular compounds that can sustain life. So all this cannot be really seen invisible, right? We need much more stronger things, right, to look at them. Yeah. So that's the biggest thing. And when a planet is so far away, if your device is not very accurate, it's very, very, very easy to misunderstand the data and to consider it as a planet. For instance, there is a mission, I think it's Spitzer, probably it's Spitzer, the Spitzer telescope. No, it's not the Spitzer. Planck, sorry, because it's from the Europeans. Many of the planets that they thought they are planets, they were actually very small stars. So improving the accuracy, it's extremely important. It's going to help us to, be sure that what we are seeing, it's there and it's what we are thinking it is. Yeah.
Okay, sorry I'm late. Yeah, I'm still human, unfortunately. So, but anyway, okay, thank you so much for being here today. And it's encouraging to see such a great audience. I would like to thank the Art Science Museum for organizing this amazing series of events. And I'm honored to be able to share some of the intricacies about the industry with all of you today. All right, so can I ask you a question? Apart from all those places being in Singapore, what do they have in common? Anybody? It's not a trick question, it's actually quite straightforward. Okay, they are all quite new actually. Yeah, they have not always been around, and yet over the last couple of decades or couple of years only, they became the driving forces of our economy. So what do you think is coming up next? Well, I'm biased, but I like to think it's space. And we are in a very good position to jump on the new space race. I'll explain to you the characteristics of it in a moment, and then I'll show you just how possible it is, how realistic it is. It's no longer the same era as the Apollo program, and we no longer need budgets as bloated as NASA had back then. So we have a very good chance. But before then, let me explain to you a very, very important difference between two things that people very frequently confuse. What is the astronautics versus astronomy? So astronomy is essentially the study of the night sky. It's the study of objects in the universe. It's creating a map that helps us navigate and understand the universe better, that helps us understand the solar system. Astronautics, however, is an engineering discipline of traveling in space, of actually developing spacecraft and sending them beyond Earth. So the two of them very often overlap, actually. Many space telescopes require the engineering of astronautics to be actually sent up. Much of our understanding of the non-visible light spectrum comes from satellite-based telescopes, because much of the electromagnetic spectrum doesn't actually penetrate the atmosphere, so we rely on it very heavily. Conversely, you could say that robotic probes, such as the Mars rovers and the planetary probes, were also helpful in developing our understanding of astronomy. So what is the key differential here? Astronomy relies on public funding, and it's a scientific field. It's an extremely important one, but it's astronautics that's actually a business. It generates money. And how much money are we talking? Well, a lot, because it helps us solve very, very down-to-earth problems. Satellites are actually all about collecting data and transmitting data in many different ways, with many different technologies on board. But the most important things which come from that is connectivity. It's knowing what's going on around the planet. It's understanding what's going on currently and how this planet is changing, and that could be in a short run or could be in the long run. And also, it's about generating geospatial data, which is critical for many industries. We're talking forestry, we're talking agriculture, we're talking mining, logistics, maritime, aviation, of course military. So there's a lot of real-life applications to space technologies. So now let me explain to you a little bit about how the industry actually operates. What is the structure of it? So, of course, there's lots of supplementary organizations and services. There's, of course, there's things like the legislation, the regulatory support, which comes mostly from governments. There is also things like space insurance, actually. You can insure your satellite in case something goes wrong, so you can get your payout if it does. Some forms of insurance are even compulsory, like for rocket launches, in case something gets destroyed in the process. Liability insurance is actually mandated by every single jurisdiction. So there's lots of peripheral services and things in the industry. But the core comes in three forms. The ground segment, which means the receiving station that you use. And the most basic form of that is your satellite TV dish. It's not so common in Singapore, but pretty much everywhere else you will see all thousands of them for satellite television. Then comes the very representative part, the launch segment, the rockets. There is no other way to put a satellite into orbit right now rather than use a rocket. It just isn't feasible. There are some concepts which don't require rockets, but they are still very hypothetical. And last but not least is the actual spacecraft, the space segment. So, to put things in a bit of a context, this is how much space economy was worth collectively in 2017. And space economy is a very interesting, it's a bit of a misnomer because it says global space economy, but it's actually outside of the globe, right? No, logically speaking. But you can see that actually majority of the revenues are coming from things like data analytics, from what you do with all that data you gather from satellites on the ground. The launch industry is still a bit of a bottleneck. It was only worth about 4.6 billion, actually, for all those rockets which are being sent up. But nevertheless, that industry is our focus as my company, and it is poised to grow significantly because there is so much demand coming up for very novel ways to generate and transfer all that information. So, we are living in what's very commonly referred to as the new space era. It's a very popular buzzword in the industry. So let's characterize it a little bit. The old space relied on very, very heavy satellites. We're talking a couple of tons per launch mass. Those things were very, very expensive to build, even more expensive to launch. A single campaign could take a couple $100 million just to put up a single geostationary satellite into space. But the same thing which has been affecting our phones and our computers have also been affecting satellites. They get cheaper, more efficient, smaller. If you compare a modern smartphone with a Nokia 3310, you know what I mean. And the same thing has been affecting satellites. And no longer do you need to spend hundreds of millions of dollars to put a network of satellites. These days we have very novel platforms, such as the ones you can see in the other gallery, which take a couple $100,000 to build. And they can increasingly perform same functions as the very heavy and expensive, bulky satellites of the past. So it really changes the entire paradigm in connectivity. In many cases, it becomes more cost-effective to send a fleet of satellites into orbit than to build a fiber network across an archipelago of islands, for instance, which is very interesting. That means that there's more money and more interest shifting towards space tech. So, to put things in a context, we're looking at smaller ground segments because you no longer have to reach out so far as geostationary orbit. Most small satellites, the CubeSats, are only in a few 100-kilometer altitudes. They are actually not that far. And as a result, you don't need so much power for the two-way communication with them. The launch vehicles are also changing dramatically. What you see on this picture is the Electron from Rocket Lab. It's a New Zealand company, and New Zealand actually has launch capability right now. That's incredible. And it only popped up a couple of years ago. And the reason why you want a smaller launcher is because with a smaller satellite, you can choose exactly which orbit you want to go into and exactly at which time. If you want to do testing in space, let's say you have a flock of small satellites and you just want to verify if they work as intended, you can do so-called ride sharing. You can put them on a single large rocket, and it works. You don't really care which particular orbit you're into. You don't care about the inclination or the orbital plane. But if you want to deploy a network of satellites, if you want to maintain global or regional coverage, you want to make sure they are properly spaced out. And the only way to do it is with smaller launch vehicles. Otherwise, the penalty for changing your orbit after launch is massive. You have to use a lot of fuel. If you've, some of you who were here yesterday would probably remember my explanations about, the relationship between velocity and orbit. And to change your orbit, you need to change your velocity, and that takes lots of fuel. Very few satellites of that size carry any fuel, and if they do, they typically don't carry enough to make any drastic course adjustments. So that's why it makes perfect sense to use smaller launchers, even though they are more expensive per kilogram, just to get in exactly where you want, and at the same time. And the space segment, I don't really have to explain much. I think everyone had a great opportunity to have a look in the other gallery. We're talking size of a shoebox or a bottle of wine, as someone whom I know likes to explain it. So, it seems like space industry is very difficult to touch right now. Because ultimately, we're still talking about very heavy investments. The barriers to entry are still very high, even though they've lowered dramatically. And ultimately, you're looking at 3 different qualities of a particular country, let's say, or a particular scene, before it can grow its successful space tech industry. So engineering talent, of course, that's the bedrock. You need prior experience, you need some heritage, and you need the resources, you need funding. Unfortunately, that's the thing that keeps me awake at night. Yeah, the reality is you think you're going to be building rockets, but in the end you just chase after people with money. All right, so, well, surprise. We do have, in Singapore, very good engineering training programs, such as the one at NTU or NUS or SUTD. We do have prior experience. We do have a bunch of satellites already in orbit. And we are famously one of the key financial hubs of Southeast Asia and indeed the world. So yeah, the funding is already somewhere there, but it doesn't really go into the industry just yet. So the building blocks are already in place, but we have to prove ourselves. Unfortunately, this is a reality of running, whether it's a company or whether it's a student initiative, you have to deliver. This is where we are currently. And Equatorial Space have been making some very good progress. This is the time when I basically just navigate towards promoting our own company. So we did some ground tests of hybrid rocket engines. For those of you who have interest in rocket propulsion, you will know that a hybrid rocket engine has solid fuel and liquid oxidizer, which means it's drastically simpler than a liquid fuel engine, but it's much safer than a purely solid-based rocket motor, because it can be shut down at a precise moment, and if something goes wrong, you still have the choice to just, also shut it down, or throttle it if you want to. Coming up soon, in the next 2 to 3 months, we have a 14 kilonewton engine test coming up, which will most likely be overseas. I don't want to share exactly where just yet, but we will be able to release that information in the near future. And last but not least, in Q1 next year, we will be doing a suborbital test, which means it will go to around 60 kilometers in altitude, and that rocket will feature a guidance, navigation, and control system, as well as live telemetry feed, which are some very important systems that you need before you develop a launch vehicle. And this is what we are working on in the longer run. Hopefully, we should be able to fly it by 2021. Location-wise, I will show it to you on the next slide. But we're looking at a full hybrid configuration, which means we would be able to significantly undercut the competition. We have access to technology which is very innovative and very promising and addresses historical problems with hybrid rocket engines. So again, for those of you who have interest in propulsion, you will know what I'm referring to. But those things were not flown because of some problems with the solid fuel before, not flown into orbit. So we're looking at a payload capacity of around 65 kilograms. It's still being studied, which basically we are still reaching out to some of our prospective partners to see what's the payload capacity they would really like to see. But you can safely say we're looking at CubeSats and microsatellites. And this rocket will be able to cost-effectively send them exactly where they should be going. It's a great opportunity for us. It could be a game-changing vehicle for the global space industry. And it could be launched from, well, 3 prospective locations that we have identified so far. And we are already in touch with the respective authorities. Frankly speaking, I think we have a highest chance in Northern Territory in Australia. The space called Nhulunbuy is very attractive. And Australia is completely revamping all of their launch regulations. And they are making them more attractive for private companies. So it's a fantastic time to be involved in this industry, really. But we cannot do it by ourselves. Ultimately, it's rocket science, and it's still very hard. And it requires lots of support and it requires lots of cooperation. The ecosystem is already growing. This very event here today is a testament. It's a testimony of the progress which we have so far made as a whole ecosystem in Singapore and indeed in Southeast Asia. We would like to see more regulatory support, which is also happening, and I am proud to reveal that we are actually in discussion with the Urban Redevelopment Authority to set up a local ground test site for rocket engines, for very small ones, but we may just be able to move our testing operations to Singapore to speed our iteration process, which is extremely exciting. And last but not least, and this is my personal wish list, I would love to see more national initiatives and some really audacious programs that would nurture the entire industry and possibly let us contribute to that as well. So, space is not just for superpowers anymore. Gone are the days when you needed hundreds of billions of dollars of budgets to make an impact. Right now, we're looking at a situation, whatever you think of Israel, they did pull off a private space mission. I mean, private moon mission. They did not land, granted, but they were very, very close. I had a chance to speak with one of the gentlemen who was involved in the initiative, and it was absolutely inspiring to hear how a small country managed to build a lunar mission for $100 million. Much of it was actually spent on the launch by SpaceX. They were the launch contractor for them. And let me check, how much was the project, Jewel? Just saying, it's not out of reach. 1.7 billion, by the way, just for the record. So space has never been cheaper and more accessible, but it's still not easy, and it will still take a lot of work and a lot of risk. But this is the right time. And I would like to invite all of you to be a part of that journey, and thank you very much for your attention.
I think we're going to keep Simon a little bit out on stage because there should be questions from curious audiences. Is there anyone who would like to start with the first one?
Don't be shy.
So why are you developing your own rocket? Tons of people are developing good liquid fuel rockets. It seems like your value proposition could actually just be managing the launch from this advantageous location.
Right, so we've explored that. And in fact, we are looking at a slightly different pivot. We're looking at possibility of selling components to other space launch companies. There's over 100 different groups worldwide working on small launch vehicles. And indeed, most of them are using kerosene and liquid oxygen for propulsion. It's a very well understood technology. However, it's not a cheap one. It's still not cheap to build a functioning cryogenic liquid fuel rocket engine. So we are exploring possibility of selling our technology, our components, and our subsystems to everybody else. And considering we are based in Singapore, it is possible on the legal side to export it out, unlike, let's say, from the United States because of ITAR. So we are working on a possible pivot, but in a different direction.
Yeah, hi. Thanks. This is really interesting. Could you talk a little bit about your business model and funding sources?
Sure. Okay, so business model is essentially to offer, I mean, in this form, assuming we don't really bring up this pivot, which I explained just now. But in current form, it's to provide launch services for satellite operators. We're looking at around, depending who you ask, between 15 and 27,000 of individual small satellites coming up in the next 10 years. Of course, many of them will not actually happen, but the market will still be very, very potent. And I like to think of ourselves not as a rocket company, but as a transportation company. Essentially, we will be providing transportation services to bring satellites into the correct orbit. And that is where the value proposition really kicks in. That's the business model. Funding-wise, okay, so far we have been blessed with angel investors who have been very helpful with our vision. And currently we are in some advanced discussions with venture capital funds to bring it to the next level.
My question is, what are the difficulties in setting up a launch site within Singapore, and are they bureaucratic or are they technical?
Okay, very good question. It's actually both. The problem with Singapore in terms of an actual launch site, I'm not talking about the ground test. For a ground test, you just attach the engine to a test stand and you let it run for some time to see how is it performing. But for actual flights, unfortunately, in whichever direction you head, you're passing over somebody else's airspace. Whether it's Malaysia or Indonesia, they would not be very, very happy with that. That's the political aspect. The practical one is just how congested the airspace and marine space is. So in fact, our original intention and plan was to develop a platform and just send it to South China Sea and launch it from somewhere there. But after we spoke with the civil aviation authorities of Singapore, they told us they are very reluctant to close down airspace for rocket launches, at least for now. So that's why we're looking at places which are more far-flung and don't have the same problem. So.
So I would like to ask, how do you stand out in the space market, and how do you push forward to go further?
Okay, so another very good question. So for those of you who are involved in the space tech industry, you will know just how competitive the space launch market is getting. So the very first approach which we have adopted is use of hybrid propulsion because of its cost effectiveness. So we want to fight and differentiate ourselves with the price point. That's the very first thing. Secondly, by choosing some of the prospective launch sites, we will be able to cover a much more broad range of inclinations for launching. Most of the small launch vehicles are being deployed from higher latitudes, which means they are only practical for polar orbit launches. In our case, we aim to be able to do both. Both equatorial and polar and any other inclination. So it's a very good flexibility to have for our clients. Last but not least, yes, this is something that everyone just won't forgive us, but we are pretty new compared to most of the other startups. To which, let me ask you how big Singapore Airlines was when it split up from Malaysian airline system compared to Pan Am, and which one is still around. So yeah, it doesn't mean that if you're starting small, you will forever be small and that you will never be able to compete with everybody else. I think, I don't really want to make it too pathetic, but I think our competitive spirit in Singapore is, to give it our best shot and just push through it with it. Okay, that was more profound than I intended, but thanks.
Victor. So we thought that we would start by introducing what we are, what we do, in a very simple manner. And we'll have a bit of a talk, some questions that we think that the audience wants to ask, and then we'll get into it. So first and foremost, I'm going to ask Victor to introduce himself and tell me what he thinks of Singapore in 20 years' time in the space industry.
Good afternoon, ladies and gentlemen. I'm Victor. I work in Singapore Land Authority. My role is in basically to capture map data, map information, and create reliable geo information or map information to support the government of Singapore. So in order to do that, we depend on a lot of satellite technology. I think two major technologies that we use very frequently. One of them is remote sensing data, be it images or other type of remote sensing data. And also, we put in place a GNSS infrastructure, a GPS infrastructure on ground that supports very high precision positioning. This positioning can go all the way up to centimeter level in real time. And this is the infrastructure that is important to Singapore for various kind of GNSS positioning or GPS positioning. I think I'll stop there first.
Thank you very much, Victor. Gillian, so what do you do, and what do you see Singapore in 20 years for space?
So I'm Gillian from SSTA. I am the project coordinator for education and innovation. I am not an engineer by training, so I'm a bit surprised I'm on this panel with two very talented and brilliant people. What I mainly do is to try and communicate space tech to people who may not necessarily be in space tech or have a budding interest in space tech but don't know much about it yet. So I try to, if you ever watch sci-fi films, there's always this one person in that film that's always asking questions like, what are you doing? Why is this for? And I basically play that role for everyone else. And where I see Singapore space in 20 years. I don't know, I barely have my mind grasped around the last 10 years. It's a bit hard for me to say what I see in 20 years. Hopefully a space agency, maybe.
And our last panelist, Mark. So a little bit of what you do, and where do you see Singapore in 20 years?
Okay, hello everyone. My name is Mark. I'm co-founder and CEO of Eliana Private Limited. And Eliana Private Limited essentially aims to design, develop low-cost propulsion systems for space. So in short, for the mass audience over here, what our company wants to do is essentially to enable agility for satellites in space. Satellites in space at this moment, they do have some form of autonomy over how they want to maneuver. But what we want to do is to allow for these systems to be accessible to commercial entities, governmental entities, anybody who wants to put a platform in space, who wants their systems to be very agile. We do the job. So for example, for SLA, I think a lot of sensing, remote sensing is very important at this moment, and it will continue to be very important for the next decade or decades to follow. Our propulsion systems essentially will allow for these satellites to obtain higher resolution data, fly closer to Earth with higher revisit times, and make this data a little bit more sensible for analytics accordingly. So a little bit of a background for myself as well. I think you wanted me to give an introduction. I spent 12 years in the civil service. I was with the Ministry of Education, and in fact, I'm still a civil servant. I started out as a teacher, and I continued on to do my PhD in plasma physics. So while pursuing my PhD in plasma physics, I realized that we could actually deploy plasmas in space and for space propulsion. So parts of my interests as well include plasmas for medicine and geothermal, as well as plasma fusion in Singapore. One of the projects that I also was working on very, very recently include looking at the underground in Singapore. So we're talking about deploying non-invasive methods for us to actually fully map out the subsurface, including using gravimeters. Gravimeters could be deployed on satellites, seismic methods, as well as electrical resistivity methods to actually map out the subsurface. Where do I see Singapore in 20 years, or rather for space? Well, for the past 50 years, I think we've seen a lot progressing in space since we first landed on the moon, collectively as people on Earth. SSTA has been around for about a decade, and even longer than a decade. And we believe that at this moment, for this ecosystem in Singapore, we can continue to grow this very quickly. We look at the moon, we look at Mars, but I do believe, right, with our collective expertise in both engineering, from the sciences, as well as from the economy, from the business aspect, we can even reach out further. I mean, space is the final frontier, and I believe that we can really go further than just exploring ideas of how we can put a man on Mars. We can look at really seriously consider deep space exploration. We have the capacity, we have talent, we have infrastructure. We may have an agency very soon. Let's work towards that. And the 20 years from now, I believe we can actually have much more than just having probes orbiting in celestial bodies.
Thank you very much, Mark. Just a little reach out to the audience now, just to know, what do you want to hear from these panelists? So we have someone that's in new space, someone that's trying to get into the space industry from a commercial aspect, someone that's from industry, someone who's in the ministry. So does the audience have any burning questions that you have in mind? Anyone can raise your hand? If not, then we will try and give you a bit more things to think about. There's one at the back over there.
Yeah, so I'm interested in particularly focusing on where, like, the things that you won't hear outside of Singapore. So Singapore's unique advantages or strategies, or how you're thinking about it differently than anywhere else.
I'm going to direct that to Victor first, because I think he knows.
I can't really hear the questions, but I hear that you are asking whether is there a strategy for us. I would have to answer this from the perspective of user or the usage, because in my job, we don't really launch satellites, or but from the usage perspective, Singapore government We know that we are in an urban environment, very challenging environment. We have climate change issues, transportation, so all kind of challenges that we have today. Basically, space technology is one very important area where we can use them to see how we can mitigate or resolve some of these issues. And of course, with the digitalization, we are looking at the various sensors that can be deployed into the space. The current sensor in space, a lot of them already, there are new sensors that are going to be deployed into the space, and all these sensors actually capture a lot of information for us. My team is looking into various ways of making use of them, sensing the Singapore, not just at a very low resolution, but at a very high resolution, not just in 2D, but in 3-dimensional. And the whole idea is to understand our environment, to look at the trend, and also to a large extent to be able to put in some sensors on ground as well, to work together with the space technology to monitor our development going into the future. So that part of it is pretty much in the government's roadmap, and we are moving towards that direction.
Thank you very much, Victor. Just one moment. So, Mark, without going into a promo video of your company and what makes it special, what do you think is Singapore's unique role in the space industry?
Okay, I think I'm in a good position to answer this question because I was at a meeting together with Singapore and France with the Office of Space Technology and Industry. So Singapore's strategic alignment for space is really in four key areas. They're looking at how platforms can be smaller. They're looking at small platforms essentially will be the future for space because it reduces the lead-up time required for people to put up satellites up in space. It gives commercial entities access to space. So small platforms is very, very important. Number two, they're looking at making platforms more agile. Now, agile platforms, like what Victor has mentioned previously, allows for these platforms to perform new maneuvers up in space. Now, maneuvers that were not possible before can now be performed. If we are talking about disaster sensing, something happens in a particular part in the world that we are interested in, we can call our satellites down, image at particular areas, and after we've performed the mission, bring it up, extend the lifetime. So maneuvers that were not possible before, we can do it now. The third thing that Singapore is looking at is in deploying constellations. People in the past talk about deploying singular satellites. Makes a lot of sense. You put it up at 36,000 kilometers at geostationary orbit, monitors a part of the Earth, and you have constant access over the kind of information that you want. Now, with a constellation of satellites, 100 satellites, thousands of satellites, orbiting at low Earth orbit in the equatorial plane, gives you continuous densified coverage over every part on the equatorial belt. And this makes a lot of sense if you're talking about utilizing this data for very, very novel purposes.
Wait, I'm just going to chime in here. Need Jillian play the role here. Okay, so wait, what is a constellation? Can you explain for the audience here? You have 100 satellites it's for you still. Yeah, so we have 100 satellites in equatorial orbit. What does it mean to be a constellation? Because you're using this word a lot.
Okay, so essentially for constellation, right? If we just have what's the difference from having a constellation versus just 50 satellites or 60 satellites that operate independently? Now, having a constellation, you have our colleagues from Transcelestial down there, having a laser mesh network a constellation essentially allows for a satellite which is not in a part of the world where you have a ground station at, for you to communicate the data externally through satellites and beam it down. So for example, we are in Singapore at this moment. We want to know what's happening to our assets in another part of Singapore. Typically, if you have one satellite only, you have to wait 90 minutes before the satellite comes over, makes a pass over Singapore. And if there isn't any ground coverage or cloud coverage or something like that, all goes well, you'll be able to retrieve that data. 90 minutes. If we have a constellation that allows for communication externally, you can have that data instantaneously. So that's how constellations can enable the future.
Does it mean that we can get video then, or is it just photos that we're still seeing still?
So video is really something that people are really working to doing at this moment. And you know, one of the things is I'm sure some of you travel, and you find that you're unable to use your phones because you can't communicate. There's this limitation. Now, the problem really lies in the kind of bandwidth that you get from the current systems. Now, we have people developing not just 5G, looking at developing 5G, but the 6G networks of the future. So this has to be empowered by emerging payloads that are being developed at this moment and will be deployed.
I'm going to pause again. Sorry. I'm getting lost because I barely understand what 5G is. So what is 5G and then what is 6G? What makes 6G different now? And how does it all link into space, actually? Because I'm lost. So please help me on this. You.
Okay, I'm sorry if I'm hogging the mic for an extended period of time. Okay, so essentially when we communicate in space, right, there are a few bands that are actually permitted for communication at this moment. So at this moment, people are using X-band, the K-band for typical communications. The limitation, however, really is in the rate that you can downlink and uplink, or in layman's terms is how much data you can communicate or transfer when you are speaking with your satellites. So this is the real limitation at this moment. So you were asking me, why can't we have 4K video streaming on demand? And the real reason is because for that to happen, for high bandwidth transmission of this kind of information, you're looking at deploying systems that can communicate in other bands, for example, the Q band or the V band and so forth. So these are emerging technologies that are being developed. We can test them terrestrially on ground first before we can bring them up. But this really will be the future for communications.
So it's like going from a CD to a DVD to Blu-ray.
Exactly.
I just want to add on to the term constellation. Constellation, in terms of navigation satellites, is a very important concept. Navigation satellites like GPS, GLONASS, Galileo, they don't work in single one satellite. They always work in constellation. For example, GPS, Global Positioning Satellite Systems, there is about 30 of them in a constellation, in probably 4 planes orbiting the Earth. And that's how it works. At any point of time, you need 4 of them in order to get a location. And that is a very important concept going into the future.
Okay, if I could just, what was the last point? You mentioned there were 4 things that Singapore's strategy was based on. So the third one was constellations. And what was the last point?
The last one is applications. Finding a use case scenario for what you're going to put the satellites up in space for. So without a use case to drive the space industry, it doesn't make sense for public funds to be poured into an entire sector. Applications that they are looking at this moment, as I can summarize by saying ABCDE. This is the sexy thing for a smart nation, Singapore smart nation. And ABCDE really is in people talking about A, artificial intelligence, B, blockchain, C, cloud computing, D, data analytics, E, edge computing. Now if we look at it this way, A, B, C, D, E's of a smart nation, they are really empowered by data. And how can space enable this collection of data? Space allows us to be able to acquire, communicate high-resolution data at very, very fast revisit rates in order for us to empower the ABCDEs of a smart nation. So applications really is driving what Singapore's strategic interest is.
So applications, Jillian, this is for you now. How are you reaching out to all the youth of the country then? Because we know that we have this direction, and then we know that you are doing reaching out and outreach. So how are we doing this for our youth?
So with SSTA at least, we run a lot of education programs, and primarily like a Singapore Space Challenge. If you were here yesterday, you would have heard some of our alumni from the Singapore Space Challenge talk about their experiences.
Okay, wait, I wasn't here yesterday.
Okay.
So I think the audience, most of them, I'm not sure how many of them revisited, but what is the Singapore Space Challenge?
So the Singapore Space Challenge is a technical design competition that is targeted at youths. And we try to challenge them to come up with innovative solutions to space problems, current space problems. So like currently very trending is space debris, which you've probably heard about numerous times throughout these few programs at Art Science Museum. But it's definitely a very real problem because if left alone and over time, it's going to prohibit any future expansion of the space industry. So we try to tap into the youth to find creative solutions to solve these problems, mainly because we see that when they are not limited by technical knowledge, they can be very, their ideas can be very out of the box, almost crazy, but crazy is good, I think, in the space industry, because a lot of the, I mean, Apollo 11 was like a crazy idea back then, so maybe the next crazy idea could be the solution to any future problems that we, like space
We
problems.
describe crazy ideas as moonshots nowadays, and we've succeeded in making a moonshot. So the Singapore Space Challenge trains all the kids of Singapore to harness an application, and one of the examples you gave was on space debris, right?
Yes.
So that's targeting, I think, is it secondary school, am I right?
So we target youth from the age of 15 all the way to 25. So I won't say kids because
Okay.
I'm 25 and
No one knew that.
I won't say,
Now you do.
I won't say kids. I sometimes say that, but I realize that I fall in the age range as well. But yeah, so youths, and it's a very wide age gap because while we still want the creativity, we still want some technical soundness in the projects. And it's very interesting when you see the projects from the 15-year-olds and the projects from the 25-year-olds come together in the same space because they exchange ideas and they are learning from each other, and there's this knowledge sharing that's happening that's really interesting, and I can barely like comprehend like what 15-year-olds are saying sometimes when they talk about when these kids in, okay, I won't say kids, I'm sorry, not kids, but these youths when they come and this 15-year-old youths that come and share their ideas for space solutions. I'm like, how in the world did this even happen? Like I cannot comprehend it because yeah.
So you mentioned that you give them a very complex problem. How do we take stuff out from space? And you ask kids to solve it. Kids, 15 to 25, right? So
we need to stop saying kids.
Okay, we do. So how do you actually then teach them, bringing it into the vision of Singapore? How do you equip them with the skills that they need to solve these problems?
Oof. So obviously I know space always seems very daunting. Space is daunting to me, even now, and I'm in it. So for someone from the outside looking in, it can seem something like very unattainable and very scary, but the idea of Space Challenge is that we try to make space accessible to youths. We encourage them to do a lot of self-research, but at the same time we provide mentorships, we provide workshops for them that will allow them to harness skills in the area that is required to complete the challenge, and hopefully at the end of it, so we obviously say challenge, but because it's structured like a competition, but our primary goal is to have youths interested in space tech and get them to really explore an area that can seem very unattainable and make it easy for them to understand. I won't say easy to understand, but something that's a bit more in the reach.
It's interesting that you brought up that it's a challenging area to get in. So can we hear a little bit more about, what are the challenges that you face getting into the space sector? And then, challenges are opportunities, really.
Yeah.
And I'm sure our audience here, if they're still here listening to us speak about space, they're at least interested in it. So we need to tell them what is there out there for them to solve? What problems can they solve?
So I am an arts student. I am as far from space tech as you can imagine me to be. If you asked me a year ago, where I would see myself after university, I would not have said space tech. It wouldn't have even been top 10 in the list. But for some very fortunate reason, I managed to meet the people from SSTA, and they've been, and I ended up in this job, and it's been a whirlwind, and probably the biggest challenge for me at the start was just even comprehending all the terms that's being used in the space tech industry these days. Payload, I don't know, what else?
Constellations was one of them.
Yeah, satellite constellations, payloads, remote sensing. I was like, hey, what is remote sensing? And I had to sit in my first meeting, I remember, and I was like, they were throwing all these terms around, and I was like, yes, okay, write notes. And then I went out and I went to Google. I was like, remote sensing, satellite imaging. I had to key in all the terms, and and it's been a steep learning curve, but I think it's things that, but once you actually know the terms, you realize it's not that so far out because it's actually things that affect our everyday lives. You know, it's things that we actually, like we say GPS, but I think very few people know like the full name of GPS. But it's things that's all related to space tech. So it seems very out of reach, but it's actually very much involved in our everyday lives.
Thank you so much, Julian. Yes, I was going to ask.
So, you mentioned about space challenge, and most of the time, the focus is really on the space segment. But I think that in Singapore's context, we also should focus, or should divert some of the focus towards user segment, because the usage of the space technology is very key, and this is a very large area. Maybe in future, the space challenge can also have some challenges in terms of how to use this technology, how to use the existing space data that has been a lot of them. We have to try to mine all this information, work on data analytics, and see how we can solve some of the existing challenge that we have in Singapore. I think from the government perspective, that's what we are looking for from the space technology.
Victor, while I still have you, so in terms of applications of data, do you think that the government should continue being like a major consumer from the data? Because a lot of the satellite companies are now trying to sell to governments, but do you think that that's going to change in the future, or is it still going to be very government-centric?
Yep. Remote sensing is not new. Satellite remote sensing is not new. Singapore government has started looking into this, many years back. CRIPS, Center for Remote Imaging Sensing and Processing, was set up in early 90s. And I think that the idea of CRIPS, the setting up of CRIPS, is to promote the usage of satellite imagery, satellite data, to solve Singapore's problem. But when this was started in the early days, everybody was thinking that Singapore is so small. Why do you need to look from space? If you want to see something happen somewhere, you just drive your car 5 minutes, you can reach that place. There's no need, right? I mean, remote sensing.
Is it for our mothers to look at us when we're at Tekong to see what we're doing, then making sure that kids are being taken care of?
The idea, for a large country, you can't reach that place. Remote sensing technology is very good. It saves you time. So I think a lot of the time, and from the government perspective, the usage of remote sensing doesn't really take off. It's because we are quite small. That is mainly the issue, but we are looking beyond that in terms of the usage. All these data are very good records. It keeps a good record. So go back in time. We can't go back in time. We can go there now, but we can't go back in time to look at the same location. That is one very, very good application. And some of the sensors you can't really see. You can use the sensors to capture additional information you can capture on ground. Right? I think so. These are the additional application that we are looking at, and we want to harness this out from this technology as much as possible.
So for all the entrepreneurs out there, can you shed some light about how the procurement process is like? Is it you have a problem? So SLA has a problem, and then you go out and say, we have a problem, give us a solution? Or is it normally the entrepreneurs come to you and say, we have a solution, do you want to buy it from us?
Yeah. So today, we usually need to, from the usage perspective, we usually need to have a problem, and then we need to solve that problem. We are not procuring data just for the sake of procuring the information and store them. Usually there is a very clear usage, clear objective before we procure the information.
Thank you very much. Mark, your turn. So what are the challenges that you face? Because I'm a law student. I want to make money doing space law, right? So I know that entrepreneurial companies, you need to have finance to get into the industry, you need to have backing, you need to have regulatory support, you need to have government support. And these are all the many problems that I know. But what is it, something that you've personally faced that's been hard for you to getting in?
I think for space, right, a space entrepreneur, one of the key challenges really is in funding, because there are many startups. You can just look at NUS, NTU, SMU. Startups are dime a dozen. You know, for a conventional startup, non-conventional, everything's disruptive, right? Sexy word. People are interested in looking at return of investments at the shortest amount of time. All investors are looking at that. For people in the space industry, our typical return of investment gestation period, you can ask any of the guys from Celestial, Simon, all of us face the same problem, really is in securing funding and ensuring that you have this revenue stream for you to be a good user of the funds being poured into the company. So this is one of the things that a lot of startups face. So maybe if I move into the point where you were talking about how we can better engage with governmental agencies. So in the capacity of a civil servant, I've actually engaged with a couple of agencies at this moment who require solutions up in space to solve some of the challenges. Some of the agencies that we have talked to include PUB. PUB is looking at land subsidence and detection of leakage of their infrastructure underground. We've talked to people from MSS, Meteorological Services of Singapore. They are looking at seeing how satellite systems can actually improve the accuracy of weather prediction at shorter time intervals. We have spoken to CAS, Aviation Authority of Singapore, and these people, they are looking at how we can extend the range of VHF communications on board aircraft. So we also work with other agencies that we can't speak about at this moment, but we always believe that every agency and every stat board, every ministry has their challenges. It's up to us to identify what the challenges are, or rather for them to identify what the challenges are, bring it to us and see how satellite solutions can be a viable way for us to address these challenges accordingly.
So from what I'm getting, satellite solutions are still very much for big, major government agencies. Have you ever worked with any private sector companies? I know you can't give us the names, but is there interest in that sector? Do we see something? Is it growing? Do you see more calls coming in from the private sector? There's a lot of nods there. Great.
Yes. So one of the reasons why our company is not going too much into the company itself, is able to sustain operations is really in the interest in the systems that we propose. So, for example, we talked about constellations earlier on, and constellations, we feel, actually enable a lot of the startups and commercial entities. How this is possible for us really stems from the fact that if we supply a system, a subsystem, to a government entity or a large organization, they typically will purchase like a small amount for a very niche purpose. Now, if we look at the commercial slant of things, people like SpaceX deploying a constellation of 12,000 satellites, Amazon deploying a constellation of 3,000, just securing a deal with one of these constellations will bring in a revenue stream that will immediately satisfy your investors. So this is something that our company has done at this moment. We've locked down an order of 400 of our propulsion systems with one of a constellation player. And this generates revenue, which makes it very interesting for any investor who wants to come aboard for future series of investments, if we need it.
If you need it, okay, that's very interesting to hear. Opening it up to the audience now. Does anyone have any questions that have newly fomented? There's one in the front.
Yeah, because just now they say that the 5G is in the microwave range. So microwave range, there's a certain health concerns. So there's a rising concerns of the depression and anxieties in humans. So I'd like to address, because developments in space we're going to do same as the developments in telecommunication.
I'm just going to pause there. So they mentioned a lot of bands that were being used, so the Ku band, all this. They're not necessarily in the microwave region, and even if they were, I don't think that that question is very linked into space and Singapore. So we're going to skip over that. If you have a Singapore space-related question, then let's go for it. Yeah? Is there anyone else in the audience with a question? Yes, the one at the back there.
Hi, good afternoon, everyone. Thank you for the panel. I had a question for Victor. Victor, I was curious to know if in SLA you guys are looking to use, basically procure images for satellites from different imaging companies, or do you have any projects in the future to operate your own satellites?
Do you want your own satellites? Do we have Singapore flags up there in space?
We know that there are several satellites from ST.
Yeah, but I think the question was like, does SLA have a plan to,
No,
we want to own our own?
I don't think we are such a big user, to operate our own satellites. We have to start using as many satellite imagery as possible first. I think we have not reached that stage yet. And a lot of the work today, from the mapping and from the data capturing perspective, are still very much on the ground. The reason is because we are here, we can go to the site, we can quite easily assess where we are. And we are still very much depend on fixed wing plane to capture our data. So we are not going too far high up. The reason is also because we are looking for very high resolution data rather than the satellite imagery resolution still does not really meet our high resolution mapping requirement yet as of now. So it's complementary to what we are doing. We use drone, we use fixed wing plane most of the time, but we use satellite imagery for some of our applications.
So one of the issues they are facing is that the data that satellites can give is just not accurate enough for SLA to be using it. Am I right?
It's not the accuracy, it's the resolution.
Resolution.
Yeah.
Okay.
Yeah.
Okay, so we're going to shift a bit of angle now. What do you want to tell the use of Singapore? That means on today, we are celebrating the 50th anniversary of the moon landing. It's a great humanity achievement. What's the next big step that you want to see us moving forward? Is it Mars? Is it to go beyond Mars? Because I've heard Mark say go beyond Mars, but between the three of you, what is something that you want to see in 50 years' time? Just personally, it's like what drew you to space, and this is your dream, because if not, you wouldn't be doing this as a career. Mark, maybe we start with you?
Okay, so personally, I do believe that, I think we've heard a little bit from the governmental perspective and from our agencies. They do believe that having applications in space will address their challenges, but we've spoken to many agencies, we've mentioned. No agency at this moment is really interested in putting up their own satellites. But if we look at it from a different way, it will be interesting to see how we can develop a space agency. And why this space agency is very important is because every government agency has their own requirements, which requires their own payloads to be deployed and integrated on board a platform. Imagine if we have something like a Singapore governmental satellite or consortium of satellites operated by a few agencies consolidated together. A space agency will be able to consolidate the requirements and challenges from each of these agencies, make up a constellation of platforms that will be able to deploy sensors for various applications. One of the reasons why I feel we can do this and we must do this is because we talk about satellites a lot. Things that are very close to our hearts, right? As things that cost money. And of course, we've heard about ERP being moved forward to ERP 2.0. ERP 2.0 will be enabled by platforms up in space. And I do believe that we're already going to have ERP 2.0. Why not bring on board other payloads so that we can, sense data that will be of interest to other agencies for that matter. And an agency that can consolidate all of this, I think is very doable in the near future.
That's a nice dream. Our first government satellite, ERP 2.0. Julian, on your part now. So what drew you to the industry, and what are the dreams that you always hear kids say, I want to do this in 50 years?
What drew me to the industry is, so actually earlier this year, like I said, I've never pictured myself in space tech or in the space industry. I barely even knew Singapore had a space industry like a year ago. But earlier this year, actually, I I saw an article on Opportunity, the Mars rover, and them shutting it down. And I don't know why it hit me so hard. I was actually like sobbing on the train home when I read it. I don't know why. But then I was thinking like, oh, there's all this thing that's happening in space tech, and that kind of just sparked in like a curiosity in me, and I started looking into things like that. And I was like, oh, I didn't even realize Singapore was doing so many things like this, all these like amazing things. And I think Singapore sits in a very interesting position where we are a developed country, but we are space emerging. So we have all the technology and the talent and the people and all this skill set in place, and we have all this untapped potential, which makes it very interesting to see where it's headed, because we don't know where it can possibly be headed in the next.
Where do you want it to head?
I agree with Mark. I want a space agency. Actually.
You want a space agency as well? Victor,
I really do
you
hope for a space agency.
Are you gonna be our new chairman of space agencies?
Yeah, space agency is probably is a physical agency, but I think another area that we should very seriously look into is about policy. And also, I think even now also probably we need some of these quite urgently, the policy of the space data usage or space information usage. If we talk about GNSS or positioning or location in today's context, if this information are spoofed or if this information are jammed, what kind of policy do we have in place? If we talk about ERP2 that's going to be depend on this information from the satellites, and whether will people misuse this kind of information. So I think policy is another area that I would like to look at going into the future.
Policy is an area that's very close to my heart. I want to get into space law and policy. So while we're on the policy matters, and I mean, you're from the government, so I'm not sure if you're not clear this, but Singapore has recently submitted an application to join the UN Office of Outer Space Affairs under the Committee on the Peaceful Uses of Outer Space. So now we're finally entering the international realm of policy. Is this something that, do you think Singapore will play a leading role in, or is it something that we're just going to like wait and see what's going on at the moment before we come to our position?
I'm not aware of that.
Oh, okay.
I just heard from you today.
So I mean, I saw nods among. Sorry. Then do you think that is it in the next 10 years, do you see Singapore as being something as a leader in that field, or are we going to just learn from others first before we come into our principles on that?
I do believe that the best way for us to move forward for this is really to learn and, of course, be involved while we learn. And a good way for us to get this kind of traction is being a part of UNUSA, right? So at this point, we'd say we have to remain optimistic about our position. Of course, moving forward, right? What will Singapore's position be in space policy and so forth? We see Singapore as developing in terms of how we want to build capacity for launches, for developing of proprietary peripheral technologies that we want to deploy on board satellites, right? So I think a lot of us see that Singapore has potential for us to operate as a space hub. Location is very, very strategic. We're on equatorial orbit, and what this means is that if there will be constellations up in space, we will be able to be a hub where we could actually receive, transmit data to people all around the world.
So just to clarify, equatorial orbit means we have an advantage over others in some way because we're at the equator, apart from sweltering heat and rain and thunderstorms. That's actually a good part about being here.
Yes, so being in the equatorial orbit is very strategic. I would say Singapore itself, again, is a very strategic location because we are a maritime nation, we are air hub. We're looking at us being a space hub as well. Being in the equatorial orbit essentially is enabling your satellites going up to space at equatorial orbit at around 550 kilometers low Earth equatorial orbit. It means that satellites take about 90 minutes before they make a pass and return to the same point. We call this a revisit time, right? So Singapore is very strategic because it's very nicely in the equatorial region itself. Now, what we would love to have is having launches come out of Singapore. Something that Simon can address later where you can talk to him. But launching at equatorial orbit ensures that our satellites can be deployed almost immediately, not requiring them to change planes and phases of orbit. So it's really, really strategic. The only, or rather, one of the biggest challenges that Singapore faces really is in our airspace. So if we are really going to weigh the merits of having our position as a space hub versus a air hub, right, where you have lots of traffic coming in from the different airports, it's something that we have to consider if we are really going to have very rapid launches in future.
So I'm hearing that our main constraint right now is actually our land in a way, because if we had no land constraints, then we could actually build a space hub. Is that what you're saying, Mark? Or is that what the current position is? Is it because we don't have enough land that we cannot develop into a space hub? Or
I don't believe it's the lack of land, but really it's in how the launches will affect other trades. For example, the traffic coming into the different airports. Right now, even at this moment, we already have problems building our HDB flats above a certain height because it will interfere with the air traffic coming in. So if on top of that, we are going to have space launches coming out from Singapore, this is going to be an issue that has to be addressed by the relevant agencies and master planning.
Is this something that we can work with our neighbors for then? Perhaps, work with Indonesia or Malaysia, where if we can launch with them in consortium with them, as you said, then as a regional space agency, rather than thinking from a one Singapore space agency, how about an ASEAN space agency looking beyond? Do you think that that's a possibility?
Yes, the consortium makes a lot of sense because it allows for us to really pull together infrastructure, resources, and talent that we have, and to ensure that we can drive this collectively, but also look at how Singapore can be strategically aligned to ensure that we can benefit the most out of such a consortium.
Victor, for you this time. So, I know I just breached the idea about a ASEAN space agency, but do you think that in the political climate, is it easier for us to have a regional space agency, or is it easier for us to ally with one of our existing space agencies and work with them?
I am not sure, but I thought I heard about this idea floating around in ASEAN. In the area of GNSS,
yep.
There is a regional group led by the Japanese, and there are meetings every year to discuss about the technology, the applications, to discuss about the need in this kind of technology. Singapore is part of it, and of course our need, our requirement are quite different from other countries around the region. A lot of the applications is about disaster management, agricultural applications, which we are not part of that. But we have urban challenges, transportation, port application, airport application. So our airport is one key, very important application for GNSS. So there are quite a lot of differences, even though we are all using a space technology. The ultimate usage are quite different, and coming together is not very easy because of these differences.
Jillian, you look like you had something to say just now.
I was just going to say, we always talk about being in a space race, but I think as much as the space community is racing towards a next milestone, I think there's also a lot of collaboration that's happening within the industry that is very encouraging and to see, and it's good for Singapore where we have limited resources in terms of natural resources.
So could you share some of these collaborations with the audience? Because while we were talking before this, you actually said you went to Korea, am I right?
Yeah, so I actually just came back from a 2-week training program in Korea with the Korean Aerospace Research Institute, and I think when I was there, there was 32 participants from 20 countries, and these were all space emerging countries. And I think it was a very interesting 2 weeks because we talked, a lot of it was talking about how we can help each other out to develop the space tech, not just in our country, but as the region as a whole. So there was a lot of talk about that. And we also have, Singapore is also, well, we also, SSTA itself sits on KIBO, the KIBO ABC, which is
What's
also,
that?
So KIBO ABC is, so the KIBO module is part of the International Space Station. It's the Japanese research module on the ISS.
So we actually have, in some way, have a connection to the ISS.
In some way, yes. In some way. And on this like KIBO ABC, they have Indonesia and Singapore and Philippines and Vietnam and Thailand all participating in ways that we can send up experiments to the KIBO module. And Singapore has sent up a few experiments to the KIBO module through this collaborative effort. SSTA itself, we work with JAXA to help launch
JAXA
the Japan Aerospace Agency, the Japan Space Agency. So we work together with them to help launch nanosatellites at affordable rates, which I think is great because it helps Singapore to reach out to the greater space ecosystem and by forming bonds with other people in the region.
Catching on to the affordable rates, just a rough gauge, what is affordable to send up to space? How much does it cost? So if I want to send up, let's say, 1 kilo of eggs, then how much is it going to cost me to send that 1 kilo of eggs up to the astronauts?
Maybe they can answer better than I
Do you
can.
have an idea? Oh, okay.
Maybe they can. I'm not an engineer.
Nothing is reasonable in space.
Yeah, it might sound
It's all
reasonable.
relative. It's all relative.
It might sound reasonable, but then when we say it, everybody's just like, what?
I think I was quoted once by members from SSTA to deploy modules from KIBO. So I think they will be in the best position to share how much it costs, because they revealed a figure to me. I'm not sure whether I can share.
Okay, so I'm just going to assume it's a really, really big figure, and we're not there yet. But I mean, how much would you pay then to go to the ISS? Because right now, if you want to go to the ISS, it's $60 million to get there, and then $30,000 a night, right? So how low must that figure be for you to take a trip? Okay, I'm going to go to the ISS for a weekend.
How low must it be?
Yeah, because that's eventually the amount that we need to make every kilo cost to get there.
Yeah.
So how low is your price range using today's dollars?
It would not be possible for me to, and like however low it is, it would not have been possible for me to go to the ISS. I think, there is obviously a bottom line to sending something up to space. It's going to be expensive, and it's definitely not something that currently the everyday person can afford. And I am an everyday person, and so it's something still beyond my imagination that to be able to go to the ISS. But maybe someday, 50 years, another 50 years for them to get the price down to what is then reasonable.
Objectively speaking, if we looked 50 years ago, commercial air travel was this fantasy to go from one continent to another, and yet now today we're flying like nobody's business, Europe and everything. So maybe we can see that in 50 years. Yeah. So I think we're running a little bit on time. So can I just check with the audience? Does anyone have any burning questions? Yes.
Thank you. The question is for Mr. Mark Lim. The public or private space entities in Singapore, how much are they interested pursuing or even interested in the space elevator program?
Space what, sorry, program?
Space elevator.
Space elevator program.
Yes.
Oh.
How much are they interested at all? Are they pursuing any research in this direction? Any space public or private entities in Singapore?
I mean, you addressed it to Mark. Mark, do you have any clue? Because if not, I know that there is an international consortium doing
but
a space
how about
elevator.
Singapore?
I'm not sure about that. I don't think so, not to my knowledge.
Okay.
So to the best of my understanding as well, I don't feel, or rather I don't think, to the best of my knowledge, to the best of my understanding, that there's any entities, commercial entities working on the space elevator program. I also like to say that in my interaction with the university, the Nanyang Technological University, we haven't spoken or rather developed ideas on how we can further that at this moment.
Okay, thank you very much.
Thank you. Yes.
Hi, to all four of you, do you have a favorite space-related movie or character?
Oh, this is really hard, man. But okay, Julian, you can go first.
So my favorite sci-fi book, at least, was Ender's Game. And my favorite movie so far might be The Martian. I think that one was really good, actually.
From the usage perspective, we always, when we were younger, we watched James Bond. The tracking, spy tracking devices uses. So we were always wondering, how does it work? I think the whole idea is, how does it work? Why you can track someone, in a device so small. That actually makes us, very interested in this area.
Well,
okay, for me, the movie, I like Gravity personally a lot, and it's something that I showed to students when I was teaching at Dunman High School. And the reason was because Interstellar wasn't released then. So now Interstellar has become my favorite. Why? Because of all the movies that you watch related to space, Interstellar is the most scientifically accurate. In fact, the accretion of the black holes shown in Interstellar, beautiful. It really blew my mind. And in fact, everyone has seen the image of the black hole, right? Recently was released. I think it was not as mind-blowing as when I saw it on Interstellar. And Interstellar was really amazing to me because one of my favorite physicists, who's still alive, Professor Compton at Caltech, he was a scientific advisor on board. So, I love Interstellar. If you haven't watched it, please go watch it.
Okay, I think that's a raving review for Interstellar. My personal favorite is Gattaca. It's about a guy that wants to look up into space, and you're familiar with it, but for the rest of it, it's just about a guy that wants to go into space regardless of the costs and the limitations that's placed upon him. And I think it's the kind of movie that you watch as a Singaporean that wants to be in the space industry, because you recognize that there is a lot of challenges ahead of you. We don't exactly have the best passport for this. We're not American, Chinese with a big-ass space program, but we have a decent passport, so we have a chance. And I think it's about taking that chance and running with it. So yeah, that's my favorite space movie. Any other questions at the back? Sorry, yes, there's one over there.
Thank you. Hi. So I'm quite curious about funding. Like, why do I'm not sure if you've been funded by investors already. So like when investors approach, right? Like, do they tell you the reason why they chose to invest? I mean, like for us, not average Singaporeans, right? We have NDP, we see fireworks. People already make noise about taxpayers' money blowing up, right? Like fireworks. So I'm just curious, do they give a reason? Is it for altruistic reasons, or is it because they believe in the dream? Do they explain why they chose to fund space projects?
I think this has to go to Mark, man.
Excellent question. I've met many investors. In fact, the two men in white in the front, they can attest to the number of investors we've been to. I mean, the number of decks that we had to craft for different investors for, different strategic reasons. It's really a nightmare. Okay, so what do typical investors actually look at? Sorry, again, are they investing strategically? To 99% of investors, the answer is no. The main strategic reason is return of investment. How fast can you give me back the money, and how much can you give me back the money? If the lead-up time is somewhere in the order of 3 to 5 years, they're not. Most of them will not be interested. So yeah. And okay, another thing to add as well. Most investors, or rather based locally or internationally, the kind of amounts that space tech startups require for funding for them to run operations for maybe about a year, 12 to 18 months, as compared to maybe a startup dealing with artificial intelligence or cloud computing, the figures are orders of magnitude different. So
could you give us a rough gauge so that we know what we're talking about, in terms of numbers? Because 10 and 100 is orders of magnitude, but
yes.
What are we looking at here?
So I'm just generalizing. People in fintech startups typically can operate at around $50,000 doing coding, get a nice group of people or interns, work for free. They come up with codes. And they can run and get some students from the computing engineering department to, let's commercialize this. Return of investment, maybe in about 12 months, everything's successful, like maybe Carousel or or Red Mart. Wow, millions of dollars. Space tech companies are what we require to function. There's so many of us out there. Simon and the guys from Celestial. We burn in the orders of millions of dollars. And you see, you compare $50,000, you can return on investment in 12 months versus a startup like us, we are requiring millions of dollars. When would the investors see the return of investment? I tell them 5 years, they run for the door. So yes, we have to find very strategic investors, and that's something that's very difficult to do.
Victor, for you then, because if we're looking at millions of dollars, I don't think there are many people out there that are happy to give up millions of dollars. Only the government has that kind of deep pockets. So in terms of the projects that you do pay for, the publicly available ones, of course. So when you do reach out and use the satellite data and everything, what are the numbers that we're looking at from SLA? Are we looking at millions of dollars as well? Or are we looking at something slightly smaller because we're using existing data and we're just applying it?
It really depends on the different scale of the projects. We do spend millions of dollars for very strategic reason, yeah. And also, and when we really do that, it is really not about solving one problem. It is also trying to do this whole of government. So usually, the issue is serious enough. We have enough crowd. The different agencies can share the information, can share the data. So even though the project can be quite large amount, it can cost quite a lot, but well assured that the money is well spent. We squeeze every single drop of information out from the data that we have captured, and that's how we work.
Maybe on to Gillian now. So we're talking about lots and lots of large sums of money, and you know the kids of the future are going to be the ones benefiting from it the most, right? And you talk to kids all day long, outreach to them, of course. So whenever they come to you with a project, what's the number that they're always looking at? What do they want to achieve? Is it a monetary thing, or is it something that they come to you with a social aspect? I want to use this satellite data to solve these problems, perhaps.
As in from the perspective of the youth?
Yeah, from the youth, before they become tainted with money.
So I think for the youth that actually participate in any of our programs, it's always a genuine interest. They're very passionate. They already have that interest there, and they see the programs that we run as opportunities to take that interest one step further. So I won't say for them it's very it's very driven by money, obviously. We have seen some of our youths take this knowledge and do and commercialize, like.
Give us an example, maybe.
So actually, just yesterday we had 2 of our alumni from Singapore Space Challenge, and they are taking the idea that they pitched for Singapore Space Challenge and they've started a company.
What is this idea? Is it private yet, or is it public knowledge? Can we know about this idea?
Well, the idea, I think, so what they're trying to do is to do reusable rocket launch technology. That's what they're trying to do. And they've started a company to do just that. It's 3 very bright, very young, they just graduated from Polytechnic. But with our youth mostly it's a genuine passion for space tech, and what we try to do is to build, to help them keep that passion going, so that, because we need this, obviously space tech is a very challenging industry to be in. I think we've heard, Lynette mentioned it earlier during the panel, her conversation with Luosha, that it's definitely a lot of barriers to get in especially if you want to go into the engineering and scientific end of it. And I think you need a real drive and passion for it, which a lot of our youth actually have, and it's just to help sustain that drive until they reach the point where they can actually make it a career and take it further.
Thank you so much. I know we're running up, so just closing thoughts, 2 lines you want to say to the audience about Singapore and space in the next 50 years. So Mark, just 2 lines. Yeah, 2 lines. Like your closing thoughts about this entire.
I think one of the most important things is we have to realize that if we want to drive the space economy and industry, or even towards a governmental approach, or where we want to raise up this entire ecosystem, the youths of today, the innovation that they come up with will define their generation and the generations to follow. So I am a strong believer in STEM education and promoting the sciences for engineers within to contribute back to society and for our economy as well.
Victor?
So the space technology is really very important, to many countries, and also to Singapore as a small country. And as we move forward in digitalization, in smart nation initiatives, this is one very critical sector where we all need to know how to make use of it and gain the benefit out from there.
Thank you. Gillian?
I think if you have an interest in space tech, but you think you can never be a part of it, you are wrong. I think you just there are opportunities, there are a lot of opportunities in the industry, and you just need to be a little bit brave and be a bit curious, and the doors will open up for you.
Thank you. And on my part, just space banking is one thing, space finance is another thing, space law is a thing, space consultancy is a thing. So these are all major existing jobs that are out there that you can consider if you're already working in one of these fields. Thank you very much.
Okay, hi everyone. Great. Okay, so hi everyone, I'm Yvonne. So I'm from the Singapore Space and Technology Association. So firstly, I'd like to say that, the program thus far has been really exciting. It's been really inspiring. So I'd like to thank the Art Science team, first of all. A round of applause for the Art Science team. So earlier this month, SSTA was actually approached by the People's Moon Project to collaborate, and we actually sent out, I'm not sure whether you guys saw it, so we encourage Singaporeans to submit your photos, your videos, and your stories online to this project. So this project is actually initiated by the US Kennedy Space Center, and the People's Moon will actually form a mosaic of all these photos that were submitted. And this video will be shown at the Kennedy Space Center. And later today, because of the time difference between US and Singapore, it will be shown at the Times Square in New York, Piccadilly Circus in London. So, yes, this mosaic is actually inspired by an artist, Helen Marshall. So Helen Marshall actually does a lot of such historical, momentous, commemorative moments in such videos. So she took this idea, the 50th anniversary of moon landing, and decided that this is something she would like to do. So as I've mentioned, it will be shown Kennedy Space Center in Florida, Times Square in New York, Piccadilly Circus in London, and here we get a preview before everyone does. So this will be a collection of over 10,000 images that will be shown. Yeah. Okay, so we'll come up and then we'll show you the preview of the video. And yes, enjoy the preview of the video.
Everything up? That's affirmative, flight. Tony, loud and clear. Apollo 11, this is the launch operations manager. The launch team wishes you good luck and Godspeed. Thank you very much. No, it'll be a good one. CDR, FCC, how do you read me? FCC, loud and clear. Okay, Neil, have a good one. All right, CMP on panel 2, disk verify program 2. Okay, we got data back. Radar flight looks good. Right. All right, CMP on panel 2, insert verb 75 and do not enter. Verb 75, stand by. LSP on panel 3, 4, 14, 14, forward. same thing we had. That's right, retro. Go retro. Buzz, this is Houston. Give us a reading on the 2. 160 a second. We're going down on photography on the sequence. We're going in where we go. Taking this up there. About 1 or 2 inches, although the surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. Ground mass 25. Very close to red valve, hold it on. It's beautiful. I'm going to step off the limb now. You can throttle down. Better in the simulator. It's one small step for man, one giant leap for mankind.
So all these over 10,000 images will be available online until 2024, where we anticipate that humans will return to the moon, and hopefully the first woman will set foot on the moon as well. So keep a lookout. Go to the website, thepeoplesmoon.com, where you'll be able to see the full video in about 12 hours from now. Okay, thank you, everyone.
Much fun.